Hi guys, and welcome to this lecture. In this lecture, we'll try to get an overview about ARM Cortex-M3 Microprocessor and how this processor is just the result of the evolution of ARM architecture over time. We'll try to get an overview as well about different hardware block and logic within the ARM Cortex-M3 microprocessors. So ARM started in 1985, and one of its major goals was to create low-power efficient processors families. To achieve this goal, ARM's decision was to take RISC-based instruction as baseline for their instruction encoding. RISC-based instruction are executing each one a very basic and minimal processor operation. Therefore, it doesn't require sophisticated hardware logic and design to get it fully implemented and executing, which means low amount of transistors are needed and used for such design implementation, resulting of course on low power consumption. Therefore, the instruction encoding played a big role for ARM to enhance their architecture over time, as we can see here. ARM Cortex-M3 is just a processor implementation for ARM v7m architecture. ARM v7m architecture by itself is just the result of the evolution of ARM architecture over time. Before ARM v4, the size of an instruction was 32-bit. On ARM v4 architecture, ARM introduced a new set of instructions called thumb instruction. Those instructions are 16-bit, so we start to have a mix of 32-bit and 16-bit instruction size. This mix introduced new problems and challenges for ARM. One of the major problems was how the CPU will distinguish if the instruction will be 16-bit or 32-bit after doing a branch or jump. To solve this problem, ARM first introduced new branch instruction is called BX, or branch with exchange. Exchange means that the processor will have the capability after branch to exchange his state to 16-bit or 32-bit execution flow. One important information, 32-bit instruction encoding is referred actually to ARM state. So if the processor is executing a 32-bit instruction, then it will be in ARM state. And if it is executing 16-bit instruction, then it will be in thumb 1 state or thumb state. The second point to be able to solve this problem is the address to jump to. So if the instruction within that address is 16-bit, then the bit 0 of that address must be set to 1. If it is 32-bit, then the bit 0 of that address must be 0. With this 2 point, ARM was able actually to solve this problem and create what is called interworking. So this capability to switch back and forth between ARM state and thumb state based on the instruction size. On ARM v5, ARM extended basically this exchange capability to cover other instructions like BLX, branch with link and exchange. So this instruction actually is used heavily within procedure call. And within procedure call, now we have the capability to trigger the CPU state exchange between ARM state and thumb state. Other instructions like LDR, LDM, and POP, which can be used to load and update the program counter from stack or memory, have the capability as well to exchange the CPU state from ARM to thumb or from thumb to ARM. The big change, let's say, an update that ARM did was introduced actually in ARM v6 architecture. Here we have two subsets. We have the mainstream ARM v6m, and we have what is called ARM v6 T2 architecture. T2 here stands for thumb 2. Before, we used to have, let's say, 32-bit instruction, and here are referred to also ARM state when CPU is executing 32-bit instruction, as well as 16-bit. But this is not really mixed from hardware perspective. So it has been always this distinguish between ARM and thumb 1 state. However, with the thumb 2, both 32-bit and 16-bit instruction are referring to the same basically execution state we called thumb 2. So the processor, whether it is executing 16-bit instruction or 32-bit instruction, it will be always in the same state, which is thumb 2. However, this ARM v6 T2 Cortex-M architecture with this thumb2 basically support was, let's say, introducing a Cortex-M0 Plus. So the Cortex-M0 Plus was an implementation of the subset of architecture. The mainstream ARMv6M, we have in this mainstream actually we have two processor implementation, Cortex-M1 and Cortex-M0, and there the focus was actually to have fully support of 16-bit. So ARM wanted to test actually the full capability of using full support of 16-bit without the need of real 32-bit. Even there were a couple of instructions left of 32-bit on this processor, like BX and BLX, but even this instruction are 32-bit, but they are executing actually as 16-bit instruction. This allowed ARM actually to check or to improve actually the code density and the code size by using full 16-bit instruction-based assembly code. Besides this improvement and enhancement for the instruction encoding, ARM introduced a couple of new blocks. So we have what is called Envic, Nested Vector Interrupt Controller, and this is actually, the new interrupt controller from ARM. It is mainly a real-time interrupt controller, and for ARMv6M it does support up to 32 interrupt line. We have an optional MPU, memory protection unit, and this option block is only supported on Cortex-M0 Plus. We have as well the capability to relocate the vector table, and the context switching on interrupt enter and interrupt exit actually now is hardware managed. So there is no more software need actually to manage this context switching, like we had it before in ARMv5 and ARMv4. Moving to ARMv7M. So ARMv7M, let's say, included all the extension and features that has been added on ARMv6M, and even extended the existing blocks and feature. So by default now, the execution state of the CPU for any instruction, whether it is 16 or 32-bit, will be always T2. We have now a rich instruction set. So in ARMv6M, there were more focus on the 16-bit instruction. Now we have, both capability, to let's say to boost the performance. So Cortex-M3 can be clocked with higher clock speeds. So besides it is low power efficient, also it is high performance compared to Cortex-M0 Plus and M1. However, of course, this increases the size of this processor in terms of gates compared to this. One small information: so this processor, this family of processor are low power efficient processor. Plus, let's say they are small processors, so they are dedicated basically for small application and use cases. Back to the Cortex-M3. So besides the support by default to this T2 or thumb2, it has been kind of extension to some other blocks that has been introduced here on ARMv6M, like the Envic. So now we have the support of up to 240 interrupt line. The MPU is present as well, and it can cover up to 8 regions. The hardware, let's say, manipulation or hardware based context switching of interrupt, enter, and exit also still there and fully managed by hardware. And many other features that we are going to see and explore basically within the next lecture and slide. Here we can see an overview about the Cortex-M3 block diagram. First of all, we need to distinguish between the Cortex-M3 ARM core and the Cortex-M3 CPU or central processing unit. The ARM core is the one defining or maintaining the execution flow of your program, generating the different address loaded into the program counter, maintaining the internal state and values of the internal register, and many other internal functionalities. Besides this core, we have other hardware blocks that surround this core. Those hardware blocks can be divided into optional and must-to-have. Both the core and this hardware block that surround this core are defining what is called the Cortex-M3 central processing unit. The split between the main core and those optional or must-to-have, let's say, hardware blocks help to create isolation between the basic functionality needed to have the program get executed fully, or let's say to have the basic functionality of your program executed, and between the optional, let's say, feature that the CPU can offer. Let's say restricting the access right, providing more robust, basically, way to wake up the processor from low power modes. This is one thing. Second thing, the split also help to implement what is called the modularity approach. By modularity, we mean that we may have multiple products, each one of them actually using or implementing the Cortex-M3. However, we may have one product using Cortex-M3 with MPU, as we can see here, memory protection unit, and another product with Cortex-M3 without MPU. And here, really, it depends from the requirement for each product. But the main thing is that without this modularity, as we can see in this block diagram, we'll not be able to achieve this goal and having this kind of flexibility to have product with or without certain hardware blocks. And this is also one of the strongest points of Cortex-M family. Now let's move on in details. The ARM core, as I said, is maintaining the execution flow of your program. So first of all is defining the different pipeline stages and how the instruction will be decoded and executed. This is one thing. Then it depends as well the size or the width of your prefetch buffer and how many instructions this prefetch buffer can hold. It depends as well how the instruction will be decoded and executed. Then how the result will be written back basically to external memory, and many other functionalities that we will see in detail in further lecture. Now when it's come to the option, or let's say must to have hardware block that surround the core, as I said, this can be grouped into two major groups, optional and must to have. So when it's come for instance to optional blocks, we have here like the ATM, which is stand for Embedded Trace Microcell. This one is responsible of gathering the value of the program counter and many other execution flow related information to some external, let's say, hardware module that is connected to host PC. And out of this information, let's say the application running on your host PC will generate what is called coverage report or coverage results. Now we have other optional block, which is wake up interrupt controller. So as we saw before, and as we spoke about it, the Cortex-M is low power efficient processors. This means that to have an optimal application running on it, we need to have our application running most of the time in low power mode. The technical term here when it's come to Cortex-M3, we have two really low power modes, sleep or deep sleep mode. Here for deep sleep mode, which offer, the optimal, let's say, power consumption, a lot of features and functionality will be cut off and will not be available. And at a certain moment, we need to wake up our, let's say, core from this low power mode. Therefore, especially for this deep sleep mode, ARM provided a dedicated block is called wake up interrupt controller. But this is, as I said, only if we want to have this also, this block, let's say, offer optimal and way actually to handle the different signal coming from the system on chip or from the external system connected to the Cortex-M3 to wake up basically the core from the deep sleep mode, like prioritizing which signal should wake up first, basically the core, to define basically the edge of this signals and many other optional functionality. Besides those, we have what is called memory protection unit or MPU. That one divides basically the external memory connected to the CPU, either it is an SRAM, flash, ROM, into multiple regions. So here the MPU on Cortex-M3 does support up to 8 regions, and for each region we can define different access rights, either read, write, execute, and so on. Also we can define different memory attribute access for each region. This also we'll discuss in details in the MPU lecture. So, as I said, those blocks are optional, so we may have a Cortex-M3 in another product that doesn't have or implement basically these features. Then, besides those optional ones, we have must-to-have. So must-to-have like the Envic. So the Envic in the Cortex-M3 is the one responsible of managing the different interrupts signals going to the core. So Envic stands for Nested Vector Interrupt Controller. So for example, it defines the priority for each interrupt signal, enabling, disabling each interrupt line, grouping the interrupt per priority or per group of priority, and many other functionalities. The DAP. So here we know that we need at some point to debug to see how our program can get executed in the ARM core. If there are some problems, we need, of course, to explore and to investigate what is the issue. And the better way to do this is by live stream debuggings. It means single stepping through our instruction. Checking basically the CPU register, reading or writing to the system memory. This means that we need kind of models that help us actually to access those blocks and to debug the CPU. So ARM implemented this through what is called debug access port. So this module actually is acting like an interface between the host, let's say debugger or host hardware that provide the command actually to read or write basically the memories or the CPU registers, and the internal system blocks and even the internal core register. And this DAP, of course, is must to have, because without it we cannot debug. In some cases, like for high security product, they may decide actually to remove it. But in the early stage of development, we must to have this to allow developers and testers, of course, to check basically that their code is working fine. And then in the final product and the final silicon, they may decide to remove it. But in most of the cases, it is available. This is one thing. Then we have, of course, some other stuff related to debugging, like flash patch and breakpoint unit. So this unit actually offers possibility to set hardware breakpoint, to halt the CPU, to single step, also to patch basically the code, and many other functionalities that we'll explore in the debugging lecture. We need as well some way maybe also to have very basic tracing capability. I'm not talking about the ATM advanced one, but very basic one, like just, let's say, semi-hosting. And this is why ARM offer this option through the CR-Wire viewer. So we have the possibility to, for instance, do some one-way streaming from the chip or the Cortex-M to the host machine. Even we can establish communication through this channel without the need actually to have a proper communication interface like UART, SPR, and many other peripherals outside the CPU blocks. Of course, we'll discuss this in details within the debugging and tracing lectures. Besides this, we need some memory interfaces. So Cortex-M3 is hardware-based architecture. This means basically we need a dedicated bus for the data and a dedicated bus for the instructions. So this is why we are having kind of two memory interfaces. One is handling the code and one is handling the data. And we have finally an internal base matrix. So this allows kind of interconnect between those internal hardware blocks within the CPU. So this was an overview about the Cortex-M3 block diagram. However, we'll discuss, of course, in detail the different functionality and features of each block within the further lecture. Thank you.